Welcome. It's 8th of August 2024, and I've been thinking about doing a video on some of the insights I had in my early programming career. And this was sort of things you won't necessarily find out about nowadays, or they're sort of, how do you say it? Yeah, I think in things have advanced so much in the computing field that it's going to be very hard to um, it's a sort of assumed that these things are understood or taught. They may or may not be. So I know that I find that memoirs and biographies and things of the people who are around my age, um, do find interesting, and so even though what I'm about to say may or may not be that relevant to look to people who are now currently programming, um, I've come up through the educational system. It might be just interesting to see how came through the system. So let's set it up. We're talking about the late 70s, before IBM PCs. Typically, if you had a business computer, it could have been a CPM-Z based box using either a 8080 or a Z80 CPU. Ran things like WordStar, various other things, and that would be the sort of environment you were in. For my final project at university, part of my undergraduate course, I was took on basically adding backtracking to the fourth programming language. And the fourth programming language was running on a Z80 NASCOM 2, which was a small board about this size. And the interesting thing there was that this was, I believe, an original Z80 source from I think Chuck Moore, who invented the language. So it's a very simple system. Can be very compact. So I learned a lot about how to do simple things like actually writing compilers and programmable systems, very simple virtual machines, and that thing. So my computer, actually that time would have been either a mainframe I was using, a CDC mainframe at the computer center. I was in Department of Computing. Or a PDB-15, or this NASCOM. I try to remember where the NASCOM was at the time in terms of where in the Department of Computing it was in. But anyway, so I did the Z80 assembler. So I was cross-assembling probably from the CDC mainframe, downloading over a serial link at probably 300 baud, maybe 9.6K, one of the two. So that's the sort of thing. Later on, early 80s, I got a 48K Sinclair Spectrum, which is also a Z80 CPU. So this is a sort of machine that I had. I never had a CPM machine at home until probably the mid 80s, when we got a Tatung Einstein, which ran CPM and other things. So my brother Philip, was doing Sinclair Spectrum programming commercially, and converted the game Spin Dizzy and that sort of stuff. And we used the Tatung Einstein. It had the 3-inch drives, which are slightly narrower than the flop 3 and a quarter floppies, you well know you'd seen them. So this is a modern, as it were, floppy. The the ones that came on the Einstein were actually 3 inches, actually narrower, and they were reversible. So that was interesting. So that was sort of how I got into some of the stuff I did later on, including up to helping do some software patents. So I used some of the techniques that I'd gained from doing the Forth systems. So let's just have a quick look at what the Forth systems are like. So let's just switch to Paint. So I need to select a brush. I'll select just color, different color. There we go. So we got Forth. So Forth is a very simple system, and it has 3 main pieces. Let's just get rid of that. So it has, let's see if I can write within a stack. So a stack is a simple way of storing data which doesn't require registers. Basically, a stack is a pile which of data. We have a top element, and then you have the one underneath it, and the one underneath that, etc. The stack can be empty. That's no data on it at all. It also has a dictionary. So what it does is it takes the user input in whatever format it's from whatever it's coming from, and basically divides it into space separated or white space separated strings. And for each string, it looks it up in the dictionary. So the dictionary has basically a head, or the current top of the dictionary, and basically it's either a list or an array of entries, where each entry is a word that the language understands, and each dictionary entry for a word has a pointer to the code to execute for that verb or word. This is a very simple system. So basically it is get a word, look it up, get the next word, look it up, execute it, get the next word, look it up, execute that. There's no other syntax involved, so it makes programming very simple. So let's get rid of that. So the last thing really, is the third part of what makes Forth really powerful is let's see if I can. Oops. Threaded code, and this is just simply when a word is looked up in a dictionary. Normally there's a pointer to the code to execute, and when you're interpreting, which is the default, it just calls that subroutine to do whatever that word does. If it's in compile mode, what it does, it just sticks that address of that in the next place in where it's compiling, and so you end up with just a simple list of addresses initially, pointing to the code to execute for each step. This is very simple. It literally allows you to work in a very simple virtual machine, and then in the sense that the dictionary defines all the words or functions that the virtual machine understands. There's only one thing that's not in the dictionary, and that is when you get a number. So when you get a number on the in the input, which is basically a word that's not in the dictionary, if it looks to see if it's all just digits, and it will convert it into a number using whatever the current base is set to, which starts off as 10. And then we'll just put that number on the top of the stack, push it on the top of the stack. So what this means is that something as Forth looks unlike other programming languages when it's written. So you might see something like, it says something like 1, 2 plus dot. Dot is the print the top of stack as a number function. So when this is being processed by the Forth system, it sees a character 1 followed by a space, so that's the first word. It tries to look that up in the dictionary. That probably doesn't usually exist. It says, oops, it starts with a digit, and is only digit, so it converts it into the number and puts on the stack the value 1. Actually, I should probably move that down a bit, because that's not going to... Should put the stack growing up is probably easier for most people to understand. Okay. So then it looks for the next token, what's called token. So it finds a character 2 followed by a space. So it says, okay, 2, looks it up in the dictionary, doesn't find it. Says, oops, 2 it starts with a digit. It's all digits. I can convert that to a number. So in the next space in the stack, it puts the value 2. So now we have on the stack, the top of the stack is the value 2, and the next one on the stack is the value 1. So it comes along again and then says, oops, there's a plus sign followed by a space. So it looks up the plus sign in the dictionary and finds the code to do addition. And what the code that does addition does is it takes the top 2 elements of the stack and it replaces them, top 2 elements of the stack, and it replaces them with the result of the arithmetic. Lost my cursor. There we go. So it's going to put 3 on this. The top of the stack now just has the 3, and there's nothing else on the stack. And then the dot string is detected. That's looked up in the dictionary, and what that does is it just prints the top of stack out and empties the stack. Takes one element off the stack and prints it as if it was a number. So after the dot, you get the number 3. I've got to get rid of that first. So it'll output the text 3. Okay, better. I need a shortcut for that. I'm sure there is. So you'll see the output of 3, and the stack will be empty. So that's a really simple way of processing code. So what we'll do, so using that simple technique of looking things up in a dictionary, and then either, if it finds it, just executes whatever code it's told to execute. If it's not there, but it is a string of digits, it converts it to a number and puts it on the stack. If it's not that, it outputs an error message saying unknown word, basically, and basically reinitializes the stack to it being empty. So that's how it interprets. Now, when it's compiling, what it does, instead of executing the code, it just sticks that value of the code in the next position in the definition it's building. So when you're compiling, if you put 1, 2 plus when it's compiling, it does a little bit more than it does when it's interpreting, because it has to have a verb that knows how to put things from the code onto the stack. So that's usually called, there's a function called literal. And what literal does is it takes the following information from where it is in the list and puts that on to the top of the stack, and then skips that entry. So you'll get 1 plus dot. Let's just switch back to the paint. So when this code is compiled, it will generate, let's put it over here. I can't see the damn brush every time for some reason. So over here, we'll just stick it here. We'll say literal 1, literal 2 plus dot. And so that's so this is so when it's executing the compiled definition, it executes the literal code, which looks at the next place in the list, puts this on the stack, onto the stack. Then it skips down to this one. Literal again says, okay, what's the next entry? Puts that on the stack. Skips that entry, so this is then executed. The plus code takes the top elements of the stack and generates a result, and then the dot code takes the top of the stack and outputs it. What am I doing? Going the wrong way. Come on, camera. This is where I do. For some reason the camera doesn't want to reset back. There we go. Not sure why the camera doesn't always come back on. I've told it to deactivate when it's not being used, and so it should be reactivating every time I switch back to it. So apart from the literal sort of extra code, which you wouldn't normally use when you're running, actually just interpreting, it's only used when you're compiling. There's also an if test and a skip. So literal effectively takes the next element, and then we use it called skip, which just causes the sort of the program counter, the fourth program counter, to jump over the next entry it would have otherwise executed. And there's also a jump instruction, which basically takes the fourth program counter and takes the next entry and sets the program counter to that value. So it can, instead of just moving on by 2, like a skip does, it can move to anywhere else, forward or backwards, within the fourth code. So this is a very, very simple system. On an 8086 back in 1980, you could fit the compiler and the dictionary and everything else in 2 kbytes. On a Z80 like the Sinclair Spectrum, on something like this, again, it can fit in a couple of kbytes. Now that was using a very simple, what's called threaded code, where you have a list of addresses. There are three or 4 ways of using those addresses. The addresses can be the address of a subroutine, so what's called call it, and so the code you execute ends with a return instruction. It can also be what's called It can also be direct threaded, which means that the code just jumps to that address, and then the code, when it gets to the end of the jumps back to the main fourth loop that's doing the instruction execution. Then using that mechanism, you have to do this when fourth calls another fourth verb. Obviously you have to do the stacking of the return addresses and things like that. You're manually as part of the code. There's a verb to do that called do it. And then there's another smaller way, where you, instead of putting an address as the next element, you have a table of these addresses. So, and you use the index of that table, which is usually a byte. So you can create a byte set of values instead of addresses, which are normally 2, 3, or 4 bytes long, depending on the architecture. So the byte-based code, you can assign the byte value to whatever number you like. So you can either just let it assign them as they're discovered, or you can preload them with other values. So for instance, the Java bytecode from Java bytecode, yeah. So the class files are compiled into bytecode. You could use the same codes that Java uses, and then make a Java style fourth executor. Or what I had available to me is I bought the book Smalltalk 80, and in that it defines the Smalltalk bytecodes, because again, back in those days, your computer literally only had a few K of memory to play with, unlike today's gigabytes. So this is has 48K of RAM, right? The laptop that's processing this video has 32 gigabytes. So that's almost 1,000,000 times more memory than this machine had. And this machine ran fourth quite happily. In fact, using the byte mechanism, at the time, I ported a C compiler I had written. So I got a C compiler running in 48K of RAM by using bytecodes. That was on the premise that a compiler that's for a language like C doesn't actually have more than about 150 functions in it, totally. So bytecodes are quite quite easy to use. So 48K is, if you use bytecodes in like a modern language version of fourth, it sort of means that your program, whole program, just can run in the CPU cache. So that's a sort of high performance programming you can do. You don't need to program directly into high level language. You can just use bytecodes, because only some small areas of most programs are executed most of the time. So those can be in a high-level language or like C, or a low-level language like assembler, whereas the rest of the logic can be in a simple bytecode orientated format, which is highly compact but doesn't run quite as fast as the specifics that your main loops run in. The other thing about a fourth system, which is not obvious, is just see if I can switch back. No, try again. Oops, wrong window. That's what the problem is. This window. There we go, got the right window this time. So, lost my chain of thought. $48K RAM, ROM, 256 functions. What was I talking about? Okay, never mind. I'll go back and start again on that one. So what I did for one of my patents was I wrote a high performance single threaded, I was going to do multi-thread, a single threaded basically proxy, network proxy. And so each function in the list of addresses was like, is a network input available? Can I read from the network? Can I write to the network? And then some other protocol decoding functions. And because it was single threaded and really small, it did fit in the CPU cache. So even on a 300 megahertz PC at the time, it could, it must have had a 64-bit, no, a 32-bit address, a 32-bit I/O bus, because it used gigabit network cards, 2 of them. It proxied at gigabit speeds, even though the CPU could barely keep up. But it had enough performance because it was sitting in the CPU cache. It didn't that it could keep up with the gigabit networking. So that's the sort of thing I did. So what I was just remembered was to do. So even with a fourth virtual machine, it doesn't have that many things that it needs to keep track of, and therefore you can actually easily write a multitasking version of fourth, where there's multiple fourth tasks running, and where you just do a simple round robin scheduler. So you need basically the interpreter pointer. Oops. So this is pointing at the current next. It points at the next thing to be executed by the fourth virtual machine. You have a data stack pointer. You have a subroutine return stack pointer. Oops. Let's try that again. Return pointer. You have then, it depends if you want to or not, and this is where you get the choices. So if you're just executing existing code, some of you've already want to do multitask something, you can define it using a single thread, all the code that you want, and then run multiple instances just by using these three data pointers. So you'll need to allocate a data stack for each of your tasks, a stack pointer for your return address stack, and then you have a program pointer so that all the threads can run in, have their own execution. So it's a very simple virtual machine. It's you don't have to do a lot of programming to do that. If you want to, you can also add what's called data top of the dictionary. So you can have each thread at its own area. So if you can define, each thread can define its own new words, which also means it needs a D-head. This is actually the name convention from the original fourth that I was looking at. They might be called something different in the ANSI fourth. And so the D-head is the start of the dictionary. D-top is the next entry where you can start adding a new verbs if you want to. So again, you're talking about a few bytes of memory, plus probably want either an array of these things or a linked list of these things. So you can do multiprocessing really easily, even on a 8-bit microprocessor. You can have multiple threads running in a fourth virtual machine. So yeah, it's the main thing I did learn about this was, apart from the simplicity and the really how small it is that one thing you can do is when you're defining a new verb, you can define the verb in a way that it when it's defined, and the next time you use it, it runs at compile time rather than being compiled. So you can basically define your own compiler verbs. You're not limited to the ones that it comes with, like if, then, else. So you can, so for instance, you can fairly easily implement struct compiler verbs that look like other high-level languages such as C or Pascal, etc. So your fourth, even though it's running on a simple virtual machine, can easily, it's not difficult to learn how to define your own compiler verbs. So, for instance, fourth by default doesn't have a case statement or a switch statement. So you can define your own switch statements. It doesn't have any variable declaration. You can't declare variables. So you can declare your own. You can have your own variable declaration routines. Like you can have your own function definitions, like Pascal argument definition. So you can do a lot of different things. They're fairly straightforward with something. This is all began back in the early 80s. So I learned a lot about how Forth is a very flexible and powerful, extensible language. No one uses it nowadays because it is a very powerful, simple, extensible language and doesn't have any of the guardrails that modern languages have. So it has even less guardrails than, say, C. So when you compile a C program, it will do some runtime checks to make sure you're not doing completely stupid stuff. Forth doesn't even have that. So if you're, it's not good initially to run native Forth on machines. But the thing about Forth is, if you use so you can write something like this in JavaScript, and with JavaScript, for instance, you can then have a simple table of functions. And so basically, if you initialize a table of 256 functions with, say, some simple just return the top of stack or don't do anything type code, it means that it doesn't matter what you execute, it's not going to crash the JavaScript. It's just going to crash the Forth virtual machine. And that's actually, again, a very powerful use of the simple technology that Forth provides. Will the camera turn back on? Nope, camera's not. Looks like if it's off for a certain amount of time, it needs to be manually reactivated. There we go. Okay. So anyway, that was waffling on about Forth and everything else. So we'll see how that comes out. Next one I want to talk about is sort of how the multi-user dungeon based on TinyMud has some even more interesting ways of processing input. So instead of just a simple dictionary lookup, it does it by having multiple dictionaries basically in the environment. And so as you move around the environment, the dictionaries that are searched change. And this is a very powerful technique. Even in Forth, you can have a way of changing the dictionary that you're currently using dynamically. So you can have a stack of dictionaries, or a list of dictionaries that you search through rather than just having one. And then by changing the order, or adding new dictionaries, you can get new functionality. Just like importing libraries or modules in other languages. But the dynamic nature of the selecting which dictionary you're going to start in provides a lot of powerful tools in a very simple way, although it's hard to keep track sometimes. But then what you can do is to implement simple message passing style things. So for instance, if each dictionary has defines a word saying I am, and you run I am, the dictionary prints out some information about what dictionary that word matched in. Then you can sort of keep track that way. So anyway, maybe I'll do the TinyMud upgraded system next. Okay, so it's end of this stream.